Upgrade embeddings without breaking answers dual write, backfill, and cutover safely. By the end, you will understand a clear practical pattern to migrate embeddings while the app stays live and search results stay sensible. I'm Professor Pi, teaching AI engineering and LLM systems with simple Python. Embedding migrations are a common pain. You train a better embedder and you want better search. But you cannot take the service down. Users must keep getting consistent answers. The challenge is both technical and user-facing. A naive swap suddenly changes nearest neighbors and surprises users. Success looks like low risk, observable changes, and a simple rollback path. The core idea is intuitive. Run the new embedder alongside the old one. Index both versions so queries can hit either. Backfill documents in small batches. Compare results. When you are confident, switch the live path to prefer new vectors while keeping a fallback to old ones. This keeps latency low and avoids a hard cut that could break user expectations. We will build a tiny PostgreSQL example that shows the whole pattern end to end. It keeps the live table readable while we prepare new vectors. And it gives an easy way to check if answers change. No deep math is required. Think of it as a safe runway for replacing your embedder. First, we create the minimal seeded database state to work from. This snippet creates a minimal working dataset in PostgreSQL using psycopg. The cursor cur comes from a direct psycopg connection and issues SQL commands. A table D is created with OV and NV pgvector columns to hold old and new embeddings for a migration. Two small documents are inserted with only OV populated to simulate a pre-migration state. Finally, a simple count query confirms that the seed completed. Having a tiny deterministic dataset makes it easy to see how changes propagate later. The printed row count validates that our starting point is correct and repeatable. Next, we make both embeddings queryable without blocking writes. This snippet prepares zero downtime querying by indexing both embedding columns with pgvector. The call cur.connection.autocommit equals true enables create index concurrently without blocking writers. Two cur execute statements build IVFFlat indexes on OV and NV using vector L2 ops, so old and new embeddings are both queryable. The lists variable controls the number of inverted lists, trading recall for speed and memory. Higher values improve recall but increase build time and RAM. The analyze command updates planner stats so Postgres can pick the new indexes. The printed lists value confirms the chosen IVFFlat granularity that shapes search performance. Now we backfill new embeddings while the old ones remain active. This snippet simulates an online backfill that leaves the old path active. It selects IDs and text where NV is still empty, then defines M2, a simple embedding function that yields 3 floats per string. The list vals formats each new vector as a pgvector compatible string alongside its ID. Execute many applies updates in one round trip, which is efficient and safe to run in the background. If your batch grows, chunking vals reduces memory while increasing latency. Fewer larger batches lower overhead, but risk longer locks per statement. The printed count confirms that all documents now have new embeddings ready. Next, we check whether queries would change under the new model. This snippet measures retrieval delta to make the migration impact visible. The query text Q is embedded with M2, then formatted as V, so pgvector can parse it as a vector. 2 psycopg queries, order by the pgvector distance operator arrow, against OV and NV, returning the nearest ID from each index. Comparing A0 and B0 shows if the top result changes under the new model, which can trigger user-visible differences. You can increase the limit to compare top K overlaps. Larger K gives a smoother picture, but adds latency. The printed IDs reveal whether the migration alters the top answer. Finally, we flip the live view to prefer the new vectors with a safe fallback. This snippet finalizes a clean cutover while preserving availability. The view D-Live exposes a single live vector LV using coalesce NV-OV, so queries automatically favor new embeddings while falling back to old. An IVFFlat expression index on coalesce NV-OV is created concurrently, ensuring ANN speed without blocking writes. A nearest neighbor query against D-Live uses the pgvector operator to fetch the top two results with the same query vector v. Once confidence is high, you can retire OV and its index. The printed live IDs confirm the new default ranking path is active and stable. This small example maps directly to a real system. The seeded table becomes your document store. The backfill pattern runs as a background job. The view becomes the single query surface your application uses. In production, you would scale the batch size, monitor latency, and run overlap checks across larger samples. Recap what it is: a dual write, backfill, and view cutover pattern to migrate embeddings without stopping reads. When to use it. Use this when you need safer swaps and visible comparisons between old and new models. One caveat: new embeddings can reorder results. Measure overlap before full cutover. Next step: tune the IVFFlat lists value and rerun the comparison to see how recall and latency trade off during migration. If short practical AI engineering helps, subscribe and watch the AI engineering videos.